Hi guys, I'm back with my lectures. I'm Mr. Joseph, your chemistry teacher. So in today's lecture, we'll be looking at rate of reaction. Our lesson objectives for today's lecture. We're going to explain and use the terms rate of reaction. We'll be looking at frequency of collisions. We'll be looking at effective collisions and non-effective collisions. Then we'll be explaining qualitatively in terms of the frequency of effective collisions, the effect of concentration, the effect of pressure, the effect of surface area, the effect of shining light changes on the rate of a reaction. So qualitatively, we'll be looking at rate of reaction. So please, I want you to pay attention and listen attentively so we can get the best from today's lecture. Now we're looking at collision theory. Now for any chemical reaction to take place, the reactant particles must collide. There must be collision between the reactant particles. Now the essence of collision is for the reactant particles to generate energy, a minimum amount of energy that is equal to what's called the activation energy or more than the activation energy. Each reaction has its own activation energy. That is why some reactions are very, very slow and some reactions are very, very fast. So reactions that are very, very fast have a low activation energy, while reactions that are very, very slow have high activation energy. So activation energy is the minimum amount of energy required for any chemical reaction to take place. It's an energy barrier that must be overcome for any chemical reaction to take place. So what happens is that what the reason the reactant particles collide is for them to generate energy that is equal to the activation energy or more than the activation energy. Once the reactant particles collide and they're able to generate energy that is equal to the activation energy or more than the activation energy, that is when chemical reaction will take place. And such collisions, what we call effective collisions, that is, those are collisions that brings about chemical reaction. Now, if the reactant particles collide and they couldn't generate energy that is equal to the activation energy or more than the activation energy, that means chemical reaction will not take place. Reaction will not take place. So such collision is called ineffective collisions. These are collisions that does not bring about what chemical reaction. So collision theory states that what particles must collide before a reaction can take place. Not all collisions lead to a reaction. Collisions that lead to reaction is what we call effective collision. Collision that doesn't lead to a reaction, we call it ineffective collision. So reactant particles must possess at least a minimum amount of energy, which is the activation energy. So the minimum energy that colliding particles must possess for a successful collision to take place is what we call the activation energy of that particular reaction. If you look at the diagram before us, no collisions, so no chance for a reaction taking place. When there's no collisions, energy is not generated to overcome the activation energy or more than the activation energy. But once there's collision, a reaction might now take place. So it's collision that brings about chemical reaction. So we can say that collision theory states that what the rate of reaction is directly proportional to the frequency of collision of the reactant particles. That the rate of reaction is directly proportional to the frequency of collision of the reactant particles. So because the essence of collision is for the reactant particles to generate energy that is equal to what we call the activation energy or more than what the activation energy. So that is when we talk about collision theory. That's the general idea on collision theory. The essence of collision is for them to generate energy that is equal to the activation energy or more than the activation energy, which are collisions that brings about chemical reactions. So it's as simple as A, B, C. Now, according to collision theory, to increase the rate of reaction, you need to increase the frequency of collision of the reactant particles. Because based on collision theory, that the rate of reaction is directly proportional to the frequency of collision of the reactant particles. So that is it. I told you that the essence of collision is for the reactant particles to generate energy that is equal to the activation energy or more than what the activation energy. So how do you increase the frequency of collision of the reactant particles? You increase the particle speed, or you have more particles present. Yes, you increase the kinetic energy. You increase the particle speed, increase the kinetic energy, or have more particles present. That means you increase the concentration of the reactant particles, so there will be more collisions. The another way you can do it is to give the particles more energy or lower the activation energy. So once you do that, there will be more successful collisions. There will be more successful collisions. The essence of collisions for the reactant particles to generate energy that is equal to the activation energy or more than what the activation energy. In fact, to gain admission to any Nigerian university, the minimum requirement is either you get 5 credit or more than 5 credit. It's just like the activation energy, which is the minimum requirement for admission, is 5 credits or more than 5 credits. So what happens is that the student will start reading, attending lesson, burning the midnight candle in order to generate knowledge, to acquire knowledge that will enable him to go into the exam, sit for the exam, and write and come out with 5 credits or more than 5 credits. So which is the minimum requirement for admission. So the same thing with chemical reaction. The reactant particles collide. As the students read, they are colliding. They attend lessons, they are colliding. Burning the midnight candle, colliding, generating energy, generating momentum, generating knowledge. So that by the time they sit for either their JAMB or WAEC or A-level exams or their Cambridge International exams, they will get the minimum requirement for admission. So what happened is that reading, burning the midnight candle, that brings about admission. That is successful reading. Reading that brings about admission. Reading that doesn't bring about admission is ineffective reading. So we have effective collision and ineffective collision. Collisions that brings about chemical reaction is what called effective collisions. Those are collisions that are able to generate energy that is equal to the activation energy or more than the activation energy. So the same thing with the student. After reading and reading and reading, and the student is able to generate 5 credits or more than 5 credits, then that student will gain admission. We say such reading is successful reading. Reading that brings about admission. After reading and reading and burn the midnight candle, and the student couldn't get up to 5 credits or more than 5 credits, the student will not gain admission. We say such reading is ineffective reading because it doesn't bring about admission. So the same thing with chemical reactions, that once they collide and once there's collision and the collision brings about chemical reaction, we call it effective collision. So the rate of reaction depends on the frequency of collision of the reactant particles. So to increase the frequency of collision, you increase the particle speed, or you have more particles present, give the particles more energy, or you lower the activation energy. So the reactant particles can collide to generate energy that is equal to activation energy or more than the activation energy. So that is the whole general idea on collision theory. So it's as simple as A, B, C. So I want to look at how you can measure the rate of reaction, how you can measure reaction rates. Now the rate of a chemical reaction can be found or can be measured by measuring the amount of reactant used or the amount of product formed over time. Now during chemical reaction, the reactant is used up and the product is formed. So there's a decrease in the concentration of the reactant over time, and also increase in the concentration of the product over time. So you can monitor the rate of reaction by trying to measure the amount of reactant used up, the decrease in concentration of the reactant per unit time, or the increase in concentration of the product per unit time. So if you look at what we have here, you can measure the rate of reaction by measuring the amount of reactant used up over time, or the amount of product formed over time. So if you have to talk about rate of reaction, the unit for rate of reaction is equal to amount of reactant used. Amount is in moles, then time is in seconds, so it will be mole per second. Or you can measure change in concentration, or can decide to measure change in concentration of the reactant over time, or change in concentration of the product, because the product will increase in concentration while the reactant will decrease in concentration. Change in concentration of products, or increase in concentration of product over time. So if you use concentration, the rate of reaction will be mole per dnq per second. Mole per dnq per second, which is the rate. So the rate of reaction of a chemical reaction can be found by measuring the amount of reactant used or the amount of product over time, because during chemical reaction, the concentration of the reactant decreases over time and the concentration of the product increases over time. The reactant is used up and the product is formed. So it can be monitored, the rate of decrease in concentration of the reactant. The decrease in concentration of the reactant can be observed or measured over time, or the increase in the concentration of the product can be observed or measured over time. So with that, we can get the rate of a chemical reaction, the rate of a reaction, how slow or how fast that reaction is. So we're looking at rate changes during a reaction. Reactions are fastest at start, and the reason is because at start the concentration of the reactant is very, very high. So once the concentration is high, there's increase in the frequency of collision of the reactant particles. There will be increase in the rate of reaction. So the reaction will be very, very fast at start and gets slower as the reactant concentration drops, because the reactants are used up and they decrease in the concentration. So the rate of reaction gets slower because the frequency of collision decreases. So in a reaction such as A and B, to give you C, A and B is the reactant and C is the product. The concentration might change as shown. Reactant A and B, the concentration decreases with time. Then the product C, concentration increases with time. From the graph, you can see that the concentration of A and B, which is the reactant, concentration of A decreases. Concentration of A decreases with time, while concentration of B also decreases with what time, because A and B are used up and C is what? C is formed. C is the product. So the concentration of the product increases with time, and the concentration of the reactant A and B decreases with what? Time, because the reactant are used up and the product is what? Formed. So we can measure the rate of reaction. We can determine the rate of reaction by measuring what? The change in concentration of A and B, which is the reactant, over time, or the change in concentration of C, which is the product, over time. Or we can measure the amount of reactant used with time or the amount of product used with time to determine what the rate of reaction. So the steeper the curve, the faster the rate of the reaction. Reaction starts up quickly because of the greater likelihood of collisions. Yes, it starts up quickly because at that point there's an increase in the concentration, so increase in the frequency of collision. Reaction slows down with time as there are fewer reactants to what? Collide, because the reactant has been what? Used up. So as the concentration increases, the rate of reaction increases. As the concentration decreases, the rate of reaction decreases. So from the graph, you can see that the concentration, the concentration of the reactant decreases with time, and the concentration of the product increases with what? Time. So it's as simple as ABC. So we want to look at the effect of concentration on the rate of chemical reaction. Once you increase the concentration of a reactant, the reactant particles, I believe there will be increase in the frequency of collision of the reactant particles. The particles collide faster. So once there's increase in the frequency of collision of the reactant particles, there will be increase in the rate of reaction, because the reactant particles will generate energy that is equal to the activation energy or more than the activation energy for chemical reaction to take place. But whenever there is a decrease in concentration of the reactant, there will be decrease in the frequency of collision of the reactant particles. So there will be decrease in the rate of reaction, because the reactant particles might not be able to generate energy that is equal to the activation energy or more than the activation energy. So increasing concentration is equal to more frequent collisions and is equal to increased rate of reaction. So when the particles are more crowded, there's higher concentration, so there's more collisions. When the particles are less crowded, there's lower concentration, there's fewer collisions. That decrease in the rate of chemical reaction. So as concentration increases, the frequency of collision of the reactant particles increases, the rate of reaction increases. As the concentration decreases, the frequency of collision of the reactant particle decreases, the rate of reaction also decreases. So increase or decrease in the concentration of the reactant particles have effect on the rate of the chemical reaction, whether the reaction will be slow or the reaction will be fast. So just like concentration, increasing pressure can also affect the rate of a chemical reaction. That means for gaseous reactions. So increasing the pressure forces gas particles closer together. Once there's an increase in pressure, the gas particles collide with themselves and also with the volumes of the container. So there's increase in the frequency of collision. So the rate of reaction increases. Many industrial processes, such as Haber process, which is manufacture of ammonia, contact process, which is manufacture of sulfuric acid, also occur at high pressure to increase the rate of reaction, but it can adversely affect the position of equilibrium and also the yield. So what happens is that the more particles there are in a given volume, the greater the pressure. Based on Boyle's law, the volume of a given mass of gas is inversely proportional to its pressure at constant temperature. So when there's an increase in the volume, there will be decrease in pressure, decrease in volume, there'll be increase in pressure. So what happens? The more particles there are in a given volume, the greater what? The greater the pressure. The greater the pressure, the increase in the frequency of collision of the reactant particles, the increase in the rate of reaction. So the greater the pressure, the more frequent the collisions. So the more frequent the collisions, the greater the chance of a reaction. So when we talk about increasing pressure, it's just like increasing concentration. But when we talk about increasing pressure, we are dealing with what? Gaseous reactions. Gaseous reaction where the reactant and the product in their what? Gaseous state. So increase in pressure leads to increase in the frequency of collision of the reactant particles, lead to increase in the rate of. So I want to look at the surface area of contact. How surface area of contact can increase the chance of collision of reactant particles, also increase the rate of reaction. So increasing surface area increases chances of collisions, so more particles are exposed. So it can affect the rate of a chemical reaction, it can increase the rate of a chemical reaction. Powder solid react quicker than larger lumps. Powder solid have large surface area of contact, so there's going to be increased chances of collision. So catalysts, for example, catalytic converter are finely divided for this particular purpose. That's why we use finely divided catalyst. In the finely divided catalyst, what happens? There's large surface area of contact, so there's increased chances of collision of the reactant particles, and there's increase in the rate of reaction. For example, granulated sugar will dissolve faster compared to a cube of sugar, because in a granulated sugar there's increased surface area of contact compared to a cube of sugar. So that is the surface area of contact is a major factor that affects the rate of a chemical reaction, because increasing surface area increases the chances of collision of the reactant particles. So there will be an increase in the rate of reaction, because the reactant particles will generate energy that's equal to the activation energy or more than the activation energy, which will lead to effective collision that brings about chemical reaction. So I want to look at the effect of light on chemical reactions. These are reactions that are influenced by light. We call this reaction photochemical reaction. These are reactions that cannot take place in the absence of light. So the presence of light affects the rate of the reactions. Now, shining a suitable light source onto some reactants increases the rate of reaction. The light, often UV, which is ultraviolet ray, provides energy to break bonds and initiate the reaction. So the greater the intensity of the light, the greater the effect, the greater the rate of reactions. So some examples of photochemical reactions are the reaction between methane and chlorine, which are free radical substitution, which take place in the presence of UV light, breaking the halogen, for example, chlorine or bromine, to form free radicals. Then other examples are darkening of silver salt used in photography, the reaction between hydrogen and chlorine, and photosynthesis. These are examples of photochemical reaction. We talk about photosynthesis. Photosynthesis cannot take place in the absence of light. The process whereby plant manufacture their own food using carbon dioxide and water in the presence of light. So these are examples of photochemical reactions that are influenced by light. So the presence of light is one of the factors that can affect the rate of a chemical reaction, can tell whether a reaction will take place or not, whether a reaction will be slow, whether a reaction will be fast. So the presence of light goes a long way to affect the rate of a chemical reaction. Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel, like, share, comment, and feel free to reach out to me if you encounter any difficulty. I'm Mr. Joe, your chemistry teacher. I'm always there for you. Please reach out to me if you encounter any difficulty. Thank you very much for listening.